Hey guys, Mr. Gibson here. So the assignment you are about to complete is called the Kami PDF Introduction. You may not know what Kami is. Basically, it is an add-on to Google that you guys get to use this year that will allow you to edit and annotate PDFs. Now, this assignment is going to let you use different tools within Kami because we're going to use it every once in a while this school year. So I want to make sure before we dive into actual biology that you guys are able to use this and are familiar with kind of the tools that are inside of it. So if you go to Google Classroom and you go to the topic that says Unit 0 opening days, we actually haven't started Unit 1 yet. We're just kind of getting used to everything. You see Kami here is an assignment. This is the Kami PDF introduction. Now, you are not going to be graded based on accuracy. It's really just if you follow along with me and do it. And I don't ask you to do it alone. I really recommend that you just kind of follow along with me and make sure you're doing everything correctly. And the content here is actually a little bit rigorous. It's a little tough. It's stuff we're going to cover in Unit 1. But I thought it would maybe help you guys to give you a little hint of it right now. So the introductions say that Kami is a Google add-on that allows you to edit and annotate PDF files. This lesson is designed to allow you to explore many of the tools that Kami offers. Like I said, we're going to use multiple tools offered within Kami. So what you guys are going to do is you're going to open the Kami PDF document. And if you do find yourself, maybe the video wouldn't work or something like that, I have instructions in there for what to do. You're welcome to use any outside resources on the internet, your parents, if you want to email me to help you complete this document, because like I said, the content is a little bit tough, but we'll get through it. So if you click on this, for you guys, I am honestly not sure if it will look like this page or if it will automatically open with Kami. If it doesn't automatically open with Kami, then you can just click this tab right up here on the top right that says open with Kami. So you're going to open that and it opens the PDF in just a second. It's taking its time today. All right, so it will open your PDF into this. And you are now actually, you cannot edit the text that's already there, but we can add text boxes, we can draw. You can see this tab over here on the left. You can select things. There's a dictionary, text to speech if you want it to read what's on the page to you out loud. You can mark on it, comment. You can add different math equation symbols and things like that. We're going to mainly use text box and draw today. If you ever need to erase anything, there's erase there. You can always embed an image. And if you're needing to sign anything, I don't think I'll ever have you sign anything, but if you ever need to sign anything, you can always draw your signature with that tab there. So first thing you will always want to do in a Kami assignment is put your name on it. Now you can't actually write on your screen unless maybe you're using an iPad or something like that. But if we have a text box selected here, font size is 14. We can always change that if you want it bigger or smaller, whatever. You can also add different colors here. I'm just going to go with standard black 14 font. Got that selected already. So I'm just going to click where I want that to go. And it's made my text box. And you can lengthen it to whatever size you want. And my name is Christian Gibson, so I would type that there. Okay? And then you can put the date to whatever date I'm having you do this. When I'm filming this video, I'm not sure what that date is yet. And then it has the instructions. So there's these things called telomeres that are tacked onto the end of your chromosomes. They're little strands of DNA. And every time your cells divide, maybe you're needing to heal a wound, or maybe you're growing and your cells are dividing, those telomeres shorten. And so what you guys are going to do is you're actually going to quantify that process today, because they shorten as you get older. And therefore, as you get older, you're not able to heal as well, and you have certain issues with your cells that we'll get into. So it says a team of scientists at the Salk Institute for Biological Studies in California are studying telomeres, which are the stretches of DNA at the end of our chromosomes that make it possible for our cells to divide. Their research shows that each time a human cell divides, its telomeres become shorter. Consequently, the cell dies when the telomeres become too short. All right, so we have a function here. The function T of n equals 8,000 minus 100 times n, in which n, the variable n, is the number of years and the function t of n is the telomere length. So that's basically just an equation to figure out the length of the telomeres. You start with 8,000 and you subtract by 100 times whatever the number of years that have gone by. Super simple. This is Algebra 1. You guys should have had this already, and if you haven't, you're going to follow along with me, and it's going to be totally okay. You're maybe going to learn some algebra today. So just very simple equations. If you have a calculator, maybe whip that out. You can even use your phone calculator probably. So yes, the function of t and n is the telomere length in base pairs, which can be used to determine a typical human blood cell is no longer able to divide. When a telomere has approximately 1,000 base pairs left in length, it loses its ability to divide. Cells can't divide anymore. So using that info, let's just answer 1 through 5. Well, number 1, we've got a little chart to fill out here. Now, remember, on a normal PDF, you can't edit the chart, but we're using Kami. And so, again, the whole point of this is not for you to, know all of this right offhand. The point of this is that you are able to just use Kami. That's really the whole point of this activity. So I'm just going to go through this with you. So here we have the age of a typical male at age 0, we have our equation 8,000 minus 100 times the number of years old that person is. And so 100 times 0 is 0. 8,000 minus 0 is, and you can see over here, 8,000. I've already made a text box and typed my answer. Now, like I said, you also have this toolbar up here at the top. You can make it bold. You can up the font. You can do all kinds, change the text color. You can do all kinds of different, basically anything you could do in Microsoft Word, you can do in here. So now we have here the age of a typical male is 1 year old. 1 year old. So our equation is changing. So I've got text box selected still, so I just can click, make a text box, and now our equation is 8,000 minus 100, but it's not times 0 anymore because this person is 1 year old, so it's times 1. Anytime you see a number next to a number in parentheses, usually we're dividing those things, or not dividing, sorry, we're multiplying those things. So 8,000 minus 100 times 1, that's just 8,000 minus 100. And that gives us 7,900 here. Cool. So we made a little text box. We can put our answer there. Now, this time, the person is 5 years old. We've got the telomere length starts at 8,000 minus 100 times how old the person is. So now it's 8,000 minus 500, which is going to give us, I need another text box here. If you need a calculator for that, go ahead and type that in. You can also pause this video whenever you need to and pick it up later. That's a cool feature here if you're virtual. And so 8,000 minus 500, correct me if I'm wrong, but I think that's 7,500. I don't teach. All right. So here, now this person is 10 years old. So if they start with 8,000 telomeres at birth, not 8,000 telomeres, 8,000 bases. Yeah. Minus 100 times however old they are. Hopefully you are following along with me, but you're also doing this on your assignment because you're going to have to submit this for a grade. It's just a simple completion grade because I'm doing it with you. So now 100 times 10 is 1,000. So 8,000 minus 1,000 gives us 7,000. So now we're down to 7,000 base pairs by the age of 10. Well, let's skip a few years. Now this person is 40 years old. So we have 8,000 minus 100 times 40. All right, 100 times 40 is 4,000. 8,000 minus 4,000 gives us 4,000. So now we're halfway through the base pairs and the telomeres, and so slowly losing that ability for our cells to divide as we get older. All right, so now we are at the age of 65. We start with 8,000 minus 100 times 65. So that's 8,000 minus 6,500. So 8,000 minus 6,500. If I'm correct, I believe that's 1,500. I'm going to put that in the calculator just to be sure. You guys are watching this and like, he's supposed to be a teacher. He's supposed to know this stuff. Make sure I'm not telling you guys wrong here. 8,000 minus 6,500. Yep, 1,500. Cool. All right, so start with 8,000. By the time you're 65 years old, on average, you only have 1,500 telomeres left in your or excuse me, 1,500 base pairs left in your telomeres. And remember, it said in the introduction, if we get down to 1,000, cells can't divide anymore. So we're getting close. We're getting on up there in age. All right. So you can fill this box in here if you want to. It's just wanting the function retyped. We'll just do it just to show again how to use that text box. You click text box and you just click where you want it to go. You can make it as big or little as you want to. So 8,000 minus 100. All right, now this is wanting us to graph our function. So we're going to take these data points and we are going to graph them now. So now at the bottom here, we need to title this and we need to include units. So over here on this axis, this is called the y-axis. Y-axis is always vertical, if you didn't know that yet. You may come in already knowing that. Sorry if I'm insulting your intelligence, but the y-axis is vertical, the x-axis is horizontal. So at the top here on the side, we've got the y-axis. On the bottom here, we've got the x-axis. And logically, we can conclude that because of how big the numbers are, that this is likely on the y-axis the number of the lengthened base pairs of the telomere. So I'm going to actually have an idea. I'm going to select this text, copy it. It's going to save me from typing a little bit. Then I'm going to go and create a text box, and I'm going to just paste that, if it'll let me, right in there. And so there, I'm going to shorten that just a hair. And there's my units for my y-axis. Okay? You always need to have units on a graph or else no one knows what in the world you're talking about. I've seen a lot of graphs on Facebook during the coronavirus thing with no units, and I have no idea what people are talking about. So here we go. Lengthened base pairs on the left, going from 0 up to 9,000. And over here on the x-axis, those are probably years. We can guess going from 0 to 80. So let's just create a new text box, and we're going to put years. Okay. You could also put, if you wanted to, you could put time in years. Just show that we're measuring time. And if that's a little close there for you, we could, maybe change the color of our text so that it stands out like that red. Yeah, there we go. So now we know exactly what we're talking about. We have our units there. It's not getting mixed in with the other questions. Okay, so lengthened base pairs, time in years, and then it wants us to graph it. So what we're going to do is what's called a line of best fit, where you're just going to graph the data points from up here, and we're going to connect them together as best as we can. So starting at 0, we were at 8,000. So I'm going to use the draw tool here. And what color do we want to use? We made our axes, our labels in red, so let's make this red. So you just click the red thing here. You can up the transparency. You can make it a little bit transparent. You can make it really dark. Stroke thickness, let's make this pretty thick. Let's go with a 6. You can play around with that, do whatever you want to. And our first point, remember at 0 years up in our chart, we had 8,000. So there's our first point. You just click, there's a point. You can click and drag for a line. You can do all kinds of things with draw. All right, so our next point was at 1 year for the male, 7,900 base pairs. So at 1 year, which is about here, we're at 7,900, which is like barely below. We're going to go right there. Why not? All right, and then now we're at 7,500 at year 5. Year 5, 7,900 or 7,500, excuse me. So year 5, we're going to go about halfway between 8,000 and 7,000. And at year 10, we're at 7,000. So year 10, we're going to be right here on the line, right here at this nice little intersection, if I can get it there. And at year 40, we're at 4,000. There's that. And at year 65, we're at 1,500. 65. We are at 1500, which is right here. And yeah, so now as we connect the dots, all right, so there's our line. Now, the next question says, is this function linear, quadratic, or exponential? It asks if it's linear, quadratic, or exponential. And so if it were linear, that means our line is pretty much a straight line. If it were quadratic, that means you have a parabola, basically. You either have it going in like a hill or it looks like a valley. It's going up. So let me just draw it for you. Don't draw this. So a linear would be a straight line. Quadratic, the graph would be like this or like this. Okay. And I don't want those anymore, so I'm going to erase them. There we go. We use our eraser tool there. And if it were exponential, that means it's increasing or decreasing exponentially. So in an exponential graph, it would start slow and then increase super fast, or start high and decrease super fast. So we're not seeing that either. We're not seeing either quadratic or exponential. Instead, let me go ahead and erase these guys. What we are seeing is pretty much a straight line. So we need to answer number 3 here. Is this function linear, quadratic, or exponential? It is linear. It's still typing in red. I'm just going to leave it for the sake of easiness. If you guys want to change yours back to black, that's totally cool. What is the y-intercept and what does it mean in this case? So the y-intercept, we already said, is the length of the base pairs. And number 5, predict the age at which cellular mitosis stops working. Well, if you remember, it's not necessarily when the length in base pairs gets to 0. If you remember from the introduction, it says that cell division stops when the base pairs get down to 1,000. So about where did that happen? Well, if you look here, it happened about 70 years of age. Okay, so based on our graph, and that's a little bit of a rough drawing because I'm not super great at getting straight lines, but we're going to go with it. Approximately or about 70 years old is when cellular mitosis stops working in human blood cells. Cool. So there's part 1. You've just filled in a whole bunch of text boxes. You've just graphed data, labeled the axes. That's a lot for a start to CAMI. Let's move on to part 2 and see what's going on. So part 2, background information on possible causes for cancer. So now we're getting into cancer, which is directly related to what we're talking about. It's basically when it's the cycle of your cells dividing kind of messes up. We'll get into the more specifics of that when we start Unit 1. But it says by activating an enzyme called telomerase, enzymes always end in ase, telomerase, some cells can prevent the telomeres from getting any shorter, thus escaping the lethal fate of most cells. So basically, it stops that process from happening, from the telomeres getting shorter every time they divide. However, if the DNA repair goes wrong, the inadequate telomere repair and accelerated telomere attrition can cause diseases such as cancer. So if stuff goes wrong with your telomeres, you can get cancer. Uncontrolled cellular growth is an attribute of cancer cells, which continue to progress through cell cycle of growth, which is G1, DNA synthesis, which is in the S phase, G2, which is the growth 2 phase. We'll get into all that, and mitosis. And don't worry if you're like, that is Spanish to me right now. I have no idea what you just said. That is totally okay. We'll get into that a little bit later. Despite some cells having shortened telomeres. Just one cancer cell can grow into a large mass of cells called a tumor. These cells grow without regard for the normal balance between cell growth and death, forming a lump of cells. In the case of malignant growth, this aggressive behavior can eventually overwhelm the part of the body or particular organ where it's located. Okay? And here you have a general diagram of the cell cycle. You're going to get really familiar with that as we go. Okay. So here we go. Lung cancer cells have a doubling rate of about 100 days, meaning about every 100 days they double. A lung cancer patient's data is shown below. So this is the data for an actual lung cancer patient. The growth of an untreated tumor can be determined using the functions. We got a little equation here. So the T of M, the function T of M, equals 3 times 1.25 raised to the M power. So whatever M is, that's the power we're gonna raise that to. In which M is the number of months after the tumor was discovered, and the function T of M is the tumor volume in cubic centimeters. With this information, complete 6 through 10. So basically what's going on here is the volume of the tumor, the size of the tumor, equals 3 times 1.25 raised to the power of however many months have gone by. So if it's 2 months, it's 1.25 raised to the second power. If it's 4 months, it's 1.25 raised to the fourth power. All right, so we're just going to plug that in and see what's going on. So here we have, the first one is done for us. 0 months after discovery, okay, the tumor size is 3 times 1.25 raised to the power of however many months have gone by, in which this case is 0. So 1.25 raised to the 0 power is just 1. Anything raised to the 0 power is 1. So 3 times 1 is 3. So the tumor size here in this patient is 3 cubic centimeters. All right. Now, after 1 month of discovery, we've got 3 times 1.25 raised to the first power. So let's type that in to our calculators. And if you don't have one out, just want to follow me, that's totally cool. Again, the purpose of this is not that you are overwhelmed with hard questions. It's that you get to use CAMI. That's really all I'm worried about here. So let's open our calculators up. We've got 1.25 raised to the first power times 3. And if I get this wrong, feel free to email me and I'll correct it somehow. All right, so I'm still using red text. I'm not going to change it. It's all right. So that is 3.75. And our units are up here in cubic centimeters. So you see the tumor has gotten a little bit bigger by 0.75 cubic centimeters. All right, so 2 months after discovery, now we've got our equation, remember, is 3, and you can use that dot. I'm honestly not sure where it is on here, but so I'm going to use the x as a multiplying symbol. 3 times, I mean the same thing, 1.25. This up here lets you make a superscript, which is super cool. I've never been able to do that before. So if you click this little tab, follow my mouse, click this little tab up here, it's going to let us make a little superscript so we can put the second power or squared. That is really neat. I'm glad that's there. So 3 times 1.25 squared, let's put that into our calculator. 1.25 squared times 3 gives us 4.69. Double checked, and that is the correct answer. So here you can see it's actually getting even bigger in size. So that's a little scary. Now, after 3 months, same thing. 3 times 1.25. Let's make a little superscript here, this little dude up here, and to the third power. This is a super useful tool if you're in math class too, because before this you weren't able to type subscripts or superscripts. So let's type that into our calculators. I'm just going to trust it. It's 5.86 cubic centimeters. So the tumor's getting even bigger. 6 months into the lung cancer. 3 times 1.25 raised to the 6th power. Let's see what that gets us. And that is, I believe, 11.4. All right, cubic centimeters. So we started out at 3, now the tumor is at 11.4 cubic centimeters. It's almost quadrupled in size, so that's a little scary. After 9 months of tumor growth, our equation is 3 times 1.25. A little superscript here so we can put our power, our exponent, raised to the 9th power, because that's how many months have gone by. And that gives us 23.44 cubic centimeters. So we started out at 3 after only 9 months. We are at 23.44 cubic centimeters. So that's grown a lot. So let's graph this now. Now, it still wants us to label the axes. So over here, we've got, this is probably the size of the tumor, all right? Anytime you have a unit like time, like months, years, seconds, hours, days, 99% of the time that is going to go on your x-axis. It's always, that's a little trick you can memorize. The time always goes on the x-axis. So we know that months is going to go here. Okay. Time in months or just months. And over here on the y-axis, this is going to be our tumor size. And it's important to put units too, because if you say, oh, the tumor is 45, I don't know what you're talking about. So we need to know that it's talking about centimeters cubed, because that is a unit of volume that tells us how big something is. All right, so centimeters cubed. I'm going to be looking for that when you guys submit these. All right, so after at 0 months, our tumor was 3 cubic centimeters. So 0 months, it was at 3. So that's our starting point. Now I'm going to go back to draw here. Let's just keep. You want to use a different color? Let's use blue. Why not? So 0 months, 3, just a little bit over halfway to 5. All right. After 1 month, so now we're at 1 month here. It's at 3.75, so a little bit closer to 5. All right, and this is going to be kind of difficult here in a second. So after 2 months, it's at 4.69, which is almost to 5. That looks like it's right on 5, but that'll be okay. All right, after 6 months, it is now at 5.86, which is right here. And then after 9 months, sorry, I skipped a month. My bad. Let me erase that. I messed it up. All right, sorry. I skipped 3 months. So at 3 months, we are at 5.86. So about here. Now, at 6 months, we are all the way up to 11.4, which is like right there. And then at 9 months, we're all the way up to 23.44, which is, I'm going to say pretty close to 25 right there. All right, so you can maybe already tell from looking, this graph is not going to be linear. So let's use our drawing tool and connect the dots as best we can. Oops, I messed up there. My mouse got snagged. Let's try that again. Connect dots as best we can. All right, and we can predict that it would keep on going that way. Now we don't have any further data up here, but if I were to guess, it would just keep going at a higher and higher rate. All right, so judging from that, what do you think we have? A linear, meaning it's a straight line? Probably not. A quadratic, where the graph looks like a hill or a valley? Probably not. Or is it exponential, where it starts out really low and then quickly accelerates, quickly goes higher? I think we have that one. So this is cancer growth happens exponentially, which is a little scary because the further it goes, the worse it gets. Exponential. Exponential, because that's what the function is, exponential. All right. What is the y-intercept? So the y-intercept here is the tumor size. And what is the size of the tumor after only 1 year? We can predict. So to solve that, our graph, because it's exponential, it'd be kind of hard to predict, right? So instead, let's just use that math equation. We've got 3 times 1.25. How many months is in a year? It's 12, right? Raised to the 12th power. What does that give us? It gives us about, and that gives us about 46.9 centimeters cubed. That's a big tumor. So that's a little scary, right? So tumor size increases exponentially. All right. So hopefully you learned a little bit about, cell division and cancer, but more importantly for today, you learned about how to play around with CAMI. All right. And if you guys have any other questions, feel free to absolutely email me. unless it's in the middle of the night, I will do my best to get back to you as soon as possible. All right. So thank you guys. Make sure to submit this with your name on it for full credit. I look forward to hearing from you.